sample presently, and it's put inside there, and water is caused to flow through the outside at constant temperature. And it's made of panels right here that are called thermoelectric converters. A temperature difference across them will generate a voltage. And then that voltage is picked up by the computer, and based on calibration, you can relate the amount of the voltage being generated to how much heat is being generated inside here.
Okay.
So then the computer calculates how much power is going in based upon the voltage and current, how much voltage has been generated as a result of that, compares it to the calibration, and normally the two are the same. In other words, the amount going in is exactly the same amount of power coming back out. But if you have an active sample, you'll get more power coming out.
Gotcha.
That's all you're looking for, is that more power. Now, once you figure out how to make the more power, then you try to figure out how to make still more power. Well, we're still working on that.
See, what I need to figure out is I need to figure out the best way that I can study the heat that's being generated.
Well, then you need a calorimeter.
Correct.
You need a way of measuring the heat energy. And heat energy can only be detected by using a device called a calorimeter.
Is there an electrolytic process happening inside this one?
Yes.
See, that's what I need to do. I need to do an electrolytic process
Now
inside.
look here. This is the electrolytic cell.
Oh, wow.
This is heavy water, T2O.
Okay.
It's got a little lithium in it. This fits down inside there, and then currents cause to pass between the anode and the cathode, causing electrolysis. And the gases that are generated go up in here, and there's a catalyst there that turns it back into water. So
What is the catalyst?
there's a whole bunch of them, but you can buy them commercially. But it's platinum on alumina, or in this particular case, it's platinum on carbon. But platinum, very finely divided platinum, on some kind of inert substrate, it could be aluminum, it could be all kinds of things, will recombine hydrogen and oxygen back to water quantitatively at room temperature.
Okay.
So it just simply turns it back, and all the heat stays in there, so that you're not losing any because of that chemical reaction.
Yeah.
So nothing leaves the cell; it's sealed. And then I can measure the temperature inside, and I can put a heat inside through this resistor to calibrate if I wish to. And I just put that in there, and I can measure the amount of power this is giving off and compare it to how much the calibration showed it should give if nothing is happening.
May I get a close-up of that?
Yeah.
Did you make this one or
Yeah.
buy it?
Yeah, I make all this stuff.
That's great. Thank you.
Yeah, I made all kinds of cells. Here's another one that's got, not so visible on the inside, but it's got a different configuration. There's a reference electrode in here that allows you to measure what's called the open circuit voltage, which gives you information about how much deuterium is in the cathode. And there's a palladium anode, and then the cathode is put in there. I can take it out with a little screw.
Why don't you put it in as a screen instead of a solid? Cheaper?
Yeah, it's cheaper. It doesn't have to be a solid. You want as high a surface area as possible, so it's
Okay.
also give you a higher surface area.
Good question. Good question.
Anyway, so that's what you have to. This is the calorimeter that I used at Los Alamos. Much more primitive and much more complicated, but
So you're way more advanced now than
oh
you
yeah,
were then?
yeah. This calorimeter here is sensitive to 15 milliwatts with 15 watts of power going into it. So, I mean, it also will. It has a Geiger counter inside, so I can measure radiation, and so it's really a very good calorimeter. It's just not running right now.
And your power supply is just a straight DC power supply, right?
Down there, that's the power supply that I used to run it.
How much power are you putting into it? 10 volts? 12
Yeah, you
volts?
usually need, at the upper end, about 10 volts, and you usually go up to maybe 1 amp, but you can usually run it much lower than that. You run over a range. The amount of cold fusion power is proportional to the amount of power being added, or at least the current being added. So as you go up to higher and higher currents, you get more and more cold fusion power out of it.
Now, are you tuning that into a sweet spot?
Yes, you can get it to a sweet spot, yes.
And that's what you're looking for?
That's what you're looking for, right?
What would your definition of that sweet spot be?
Well, a amount of power that's stable, that I can then predictably make other changes, see what happens, and big enough that it's outside the error on the calorimeter. I mean, you get up to some kind of, when you're playing with these things, they tend to be unstable, and so that's not so good. You can't study anything that way.
Right.
So after a while, it'll stabilize, and then you'll get it to a particular current, and everything will be nice and constant. Now you can start doing things to it to find out what effect they have, and that's what you're trying for.
What do you think makes it unstable?
Well, because electrolysis produces a wide variety of changes, characteristics on the surface. I mean, you're loading deuterium, you're loading lithium, you're loading all kinds of anything, oxygen, all kinds of stuff that's in the electrolytic cell is going into that surface and changing the characteristic of the surface. And that change modifies its ability to make the cold fusion reaction. So you have to get it so that it's stable, so that things are going on and going off at the same speed. Everything is loaded up. It has a steady amount of deuterium loaded into the palladium, because the palladium takes up deuterium, reaches some kind of concentration that's stable. Then you can start playing with it.
Now, when you hit the heat sweet spot, do you have an anomaly of having to chase it and then not being able to keep it in the sweet spot, or it depends on the conditions of everything?
It depends on the conditions. I've had cells that will work for a week without any problems. So, you come in the morning, turn it on, there it is. Turn it off at night, go to bed, come in the morning, there it is. Those are beautiful cells. Others you turn on, they'll stay on for an hour and crash.
And you have that cold fusion process documented here.
Yes.
Doing that.
Yeah.
That's it.
Yeah. Yeah. It's all
in that little jar. That's it.
Yeah.
And the calorimeter is registering everything.
Yes. Right.
Now, back to the crystals and the water. We've messed with hydrogen fuel cell systems and tuning it to the tone of harmonics, musical tones, tempo to get there. Okay, I've seen the sweet spot in the hydrogen fuel cells make massive energy. Okay, and then ran engines off of it with no problem. Won't stay there because the conditions around it constantly change.
Right.
So the water temperature changes, the humidity outside, the atmosphere changes outside, the pressures change. Would you relate that to the cold fusion process that you're
Absolutely.
saying too?
Oh yeah.
See,
And that is the main nut to try to crack.
That's one of the issues. The other issue is created in the first place. Now, fuel cells you can turn on pretty predictably.
Yes.
They're just not stable. Cold fusion you cannot turn on predictably. I mean, you've got to be fairly lucky to have it work at all. Then once it works, getting it to be stable becomes then the problem.
See, this is the very most important thing, because he has a lot of experience in hydrogen on demand or electrolytic cells, DC, brute force electrolysis.
I've worked with Square One Energy and Hydromax and building the controller, and the theory behind the controller is where me and Spody Odie had collaborated on for a number of years before it was actually built. by the inventor of the Hewlett-Packard LaserJet printer. If I remember right, I remember his first name, I don't remember his last name. In that, what I'm noticing is in cold fusion, in hydrogen fuel, HHO, in trying to get that sweet spot, in John Bedini's work and Chuck's work and John Hutchison's work with the crystal cell, it all comes down to the water changing and adapting to the environment so fast that you can't, that our input method of trying to keep it in that sweet spot through electrolysis, through fusion
Excuse me?
is the main nut to crack is to keep the water stabilized in that environment at that point in time of the energy sweet spot.
Yeah, well, I explain it differently. I don't blame the water. I blame the surface that where all these reactions taking place. I mean, in a fuel cell, you have a surface where the gases are combining to make water. I mean, if you're using hydrogen and oxygen as the two gases, they're combining to make water, and then the water goes off either as a liquid or as a vapor. Usually you're working at a high enough temperature, it goes off as a vapor. And that releases electrons, and then that's the current that you measure. That surface has to have the right characteristics for the hydrogen oxygen to come together. And that characteristic can change with time, having nothing to do with the water. It has to do with the surface where that chemical reaction is occurring. The water is a byproduct of that reaction. It goes off as a gas. Once it goes off as a gas, it's gone. There's, the surface doesn't even know it's there. But the surface still has to deal with these other hydrogen and oxygen that are coming in. So the action is at the surface, not the water. And the water is going off as a molecule. Water that you're talking about is the liquid. Liquid water has all kinds of different forms. The molecule does not. The molecule is simply an oxygen with two hydrogen going off at a slightly different angle. You can't change that.
In the gas state?
In the gas phase, right. But when you liquefy it, and these all come together as a liquid, they can rearrange themselves in all kinds of different ways. That creates different structure in water. Same way with ice. Ice, they rearrange themselves in different ways, and you get different forms of ice.
Right.
So, but water, gas, one form. That's it.
That's where in the lab we were testing the hydrogen fuel with the ECAT, checking the gas phase, making sure we were in the phase.
Mm-hmm.
We could be playing music in the background, and as Emoto had showed the crystals of water at different music harmonies and that coming into a state and making beautiful crystals, or a disorganized music making completely abstract crystal.
When you say crystals, how do you know that they're crystals? What are you looking at to
Ice
say
crystals of water. That
okay.
Emoto, are you familiar with his work?
Yes.
Okay.
If you have water that is freezing and you apply ultrasound to it or do it almost anything, that will rearrange the way in which the crystals flow.
Right.
That's
the angular momentum of
that's why no
molecule.
snowflake is alike.
Understood. We're in the gas form. We got an ECAT going. We know we got the max gas that we can produce by that cell and the materials. In that gas state, that's a purity of oxygen and hydrogen.
In the gas state, you have molecules of water, molecules of hydrogen, and molecules of oxygen.
Yes.
Yeah, in the gas.
And we can't get 100%, but we're there at 98%. So going into the engine environment, you have the pistons going up and down, you have different pressures, different accelerator effects, and different heat and temperature. All the biosphere comes into effect. The water changes state in the burning process. It's like you get a tune, you're running the engine, and then all of a sudden everything changes and you have to retune to get it back into the sweet spot.
Yes.
Because of the materials, as you just explained, the palladium plates or whatever you're using, it adapts to that environment. You hit the sweet spot by tuning, and then whatever happens to that environment by the material becoming active in the environment, it changes.
Yeah.
And then you lose it, or you get less efficiency.
It's almost like the material passivates to protect itself from the ultimate goal.
Do you have you thought of, or have you really figured out possibly how to keep water in that state?
Well, no. I mean, that's not my worry.
You don't think it's the water changing
No,
that's
nothing.
creating the
Nothing.
cause and effect at the
No.
change of state
No, nothing to
when
do
you
with
have cold fusion and then it disappears?
No, it's the surface of the cathode, not the water. It's the surface of the cathode.
Okay.
And the surface of the cathode is where the action is. That's where the helium is found, that's where the tritium is found, that's where the nuclear products are found. It's in the surface, not in the water.
Okay.
And the water is just simply there as a source of deuterium. Now, if you want to do gas loading, get rid of the water. You can just take the active material and put it in contact with the gas. Get the same thing. The water is just a source of deuterium.
Thank you for that.
Very valuable.
Yeah.
Thank you for that right there, because that was my confusion between the gas loading and the water. I'm like, wait a minute, what's the water have to do with gas loading, and why are they different? The water is just a liquid source of deuterium, like you said.
It's just a source of deuterium, right?
Okay.
And the beauty of electrolysis is that source of deuterium comes to the surface at a very high partial pressure, a very high activity. 1 million atmospheres, equivalent. You can't achieve that with gas loading. But you don't have to. It turns out that if you make the active material and you put it in contact with the gas at a couple atmospheres, you'll get the same amount of energy as you did in an electrolytic cell.
I wonder where that is.
So,
Well, there's a couple things with the electrolytic cells that make a point. If you put too much amperage to it, you ruin the reaction, correct?
if you do
If you put too much amperage to it,
Well, you're changing the state at that time.
you ruin the reaction, correct?
If you
Well,
put
you
too
d-
much amperage in, you get too much bubble formation. Because, see, when the electrolytic action happens, two things are produced. You get hydrogen split away from the water. It comes in there as OD minus, and so it splits away from the oxygen, and it goes either in, where it can then interact with the nuclear reaction, or it combines with another molecule or another atom of deuterium and goes on as a gas. And so as you increase the electrolytic current, you get more and more bubbles. And pretty soon, if you get too much, you get a whole bunch of bubbles, and nothing's going in. You just get bubbles of gas coming out. So you can make lots and lots of gas, but it's not doing your cold fusion reaction.
Okay, so that's another very good point of mine. When I'm looking at that, I've always said to myself, you necessarily don't want to produce a bubble. You're trying not to produce a bubble. You're trying to as you say, load the electrode, because the bubble kind of can get in the way of that
Bubble is
loading.
wasted effort.
Right.
Right.
And so that's why I asked you what the recombination material was, because I need some of that. Because
you can buy it from Alpha Azar. It's called a recombination catalyst.
probably if I typed in recombination catalyst, it would probably come up.
Yeah.
Okay.
Yeah. I mean, these are standard catalysts. The stuff I use is a standard catalyst with palladium or platinum on carbon. It's carbon fiber.
Okay.
But other people have used platinum on aluminum oxide. Works perfectly fine. they come in little pellets. I don't know if I have anything around here I can show you, but they quantitatively convert the gases back to water.
That's perfect because I want to seal up my cells instead of the water going away because I'm just losing too much water.
Yeah, that's the way to do it. Put that in there and you don't have to worry about it. Now, you have to make sure that you put enough in there and also that it doesn't get saturated with water. Because as it starts to convert and the water accumulates, then the water can't get to the catalyst any longer. So you want the catalyst to get hot enough that it boils the water off because that makes energy that when those come together. So that it keeps free of liquid water. So you want to make sure the liquid water can get out of there.
Okay.
Away from
That makes sense. It's like wetting down a catalytic converter. If it's too wet, it's not going to work. It's got to be dry.
it. Anyway, so I do my own glass blowing and I have a good balance there. And
Oh, wow.
I have a lathe and a milling machine.
Sir, you are unique in your own kind.
I wish I never did glass blowing. I would have brought my I have this huge beaker and the vacuum port's broken off the top. I need to get it fixed.
Yeah, well, it might be a little tricky to repair, but I do Pyrex glass blowing.
Okay. It's a Pyrex beaker.
Yeah, okay.
Yeah. So this is the inside of one of your reactors?
Well, there's not much to see there. That's just junk that I'm.
How come it's black?
What is black? What are you talking
The
about?
inside there.
Oh, it's probably was used to evaporate stuff,
Okay.
so it's accumulated crud on the surface.
Well, you know what that crud is. You can look at it in your microscope at least.
Well, I can, but generally it's crud, and crud's not all that interesting.
Right. This has been enlightening. Appreciate you showing me this and taking
Anyway,
your
this thing
time
is-
out of the day to do this.
Right now, let's see what it's doing here. It's keeping track of the pressure, the temperature of the target, and the voltage being applied. And looks like it's got nice and stable. To keep a running commentary on
So
what's going on.
you're pretty much in touch with all the guys in cold fusion,
Yeah.
and I'm not. Blacklight power, they do anything?
Well, Blacklight Tower is not sympathetic to cold fusion. Randy Mills doesn't believe in cold fusion, and
He believes in his hydrinos.
he believes in his hydrinos. Now, he has produced evidence for a nuclear reaction in the past, which he denies, because he doesn't want to get tarred by our reputation. He's got enough of a problem.
I could see that. He just wants to avoid that subject, call it something else, and if he gets a reaction, then let everybody else say it's cold fusion after he gets his money.
Right. Well, he's got his hydrino, and now he's got another technique for generating energy that probably does involve a nuclear reaction,
You mean the solid
but
metal
yeah,
fuel,
right.
which was an absolute waste of my afternoon, in my opinion. I watched this whole thing, and he sparked it between a spot welder.
Yeah.
And I'm saying to myself, I get just as much energy from my spot welder when I use my spot welder. But that was kind of a waste of my afternoon to watch
well,
that.
He claims he's making a much higher temperature than we'll be able. He does it in the absence of the water containing material. He gets a spark, and then he puts the water containing material in there, hydrogen containing material, and gets an enormous spark. So he claims that he's making extra energy.
How long will you run this reaction?
So we'll see what happens, because
A couple of weeks? How long will you run this one?
it takes about 24 hours to put down a useful amount of material.
Okay.
I just turned this on in the morning. This is run for a little over 4 hours.
Good. So that's a good timing.
And this is the test bed on this side.
On that side, I can test whether or not it's accurate. And this is a vacuum system.
Testing
here.
the radiation. This is vacuum.
And that's vacuum. And this is allows me to test the radiation.
How much vacuum are you pulling?
It goes down to below 1 times 10 to 174. It's a little molecular pump in there.
Is that below 13 pounds of vacuum, or I'm only on the no vacuum by sucking down an AC system?
Right. The pressure, atmospheric pressure here is 573 milliliters. This is pulling 10 to the minus 7 milliliters.
If it was converted into inches of vacuum, what would that be?
Well,
I think that's the question.
0 inches, I mean, it's, from inches would be 10 to the minus 10 or something like that. Right now, the pressure here is 22.5 inches of mercury.
That's the atmosphere.
That's the atmospheric, right? We're at 8,000 feet, so you don't get the full atmosphere.
Huh. So you're like in the perfect spot, best spot for doing this.
Right, it always starts at a lower
no
pressure.
water in the atmosphere, and
Right. Yeah, it's very handy.
huh.
Thank you very much for showing me this. I appreciate it and your time. I'm going to cut this